Hello everyone, welcome to JCE Connect. In this particular session, I will be discussing about module number 5, that is flow through pipes, the syllabus content, introduction, major and minor losses in a pipe flow, then the Darcy-Weisbach equation for head loss due to friction in a pipe, then pipes in series, pipes in parallel, equivalent pipe problems, minor energy losses in pipe flow, then equation for head loss due to sudden expansion, then numerical problems, then hydraulic gradient line, then energy gradient line, then the pipe networks by using Hardy-Cross method and numerical problems. So this module also includes the surge analysis in pipes, means the water hammer in a pipes, then the equation for pressure rise due to gradual wall closure, and also sudden closure for rigid and elastic pipes, and numerical problems on water hammer in a pipes. Then coming to the flow through pipes. So flow through pipes is an important engineering problems in fluid mechanics. So that is this flow through pipes is one of the most important application of the subject fluid mechanics. Almost in all our daily operations we come across pipe flow. For example, water is supplied on our homes from overhead tank through pipes. Even in a large city, water is distributed through a piping system. And the most challenging task of a hydraulic engineer is to provide the flow of a liquid at desired quantity and also to find the power requirement to maintain the flow. Even sometimes the sewage flows also we classify as a flow through pipes, and even the pipe flow is also used for the transportation of chemicals and petroleum products in different chemicals and oil industries. And especially the flow through pipes, whenever the fluid starts flowing through a pipe like this, it will be under pressure. So that is, the pipe flow under a pressure is used for a lot of purposes. So here when we call uh, the fluid is flowing through a pipe, it means there is a energy gradient between the 2 points. Means suppose if this is the pipe, consider section 1 and section 2 here. So if pressure at 1 is greater than pressure at 2, then the fluid will be flowing from section 1 to 2. Hence we call as there is an energy gradient, that is a pressure energy gradient. And a fundamental understanding of fluid flow is essential to almost every industry which is related with one chemical engineering or a mechanical engineering or a civil engineering field, even aeronautical engineering also. So if you take in a chemical engineering field, so in the chemical and manufacturing industries, a large flow networks are necessary to achieve a continuous transport of products and the raw materials from different processing units. And this requires a detailed understanding of the fluid flow in a pipes. Energy input to the gas or a liquid is needed to make it flow through the pipes also. And this energy input is needed because there is a frictional energy loss, also called as a frictional head loss or frictional pressure drop. And this is due to the friction between the fluid and the pipe wall and also the internal friction within the fluid. So in pipe flow, substantial energy is lost due to friction resistance. So here, so this is the velocity profile of the fluid flows through the pipe, and one is the laminar flow and another one is the turbulent flow. So okay, so one of the most common problem in fluid mechanics is the estimation of this pressure loss. Okay, so as I discussed previously, there is an energy loss in a pipe. So one of the most common problem we come across as a hydraulic engineer in fluid mechanics is the estimation of this pressure loss. And calculating pressure losses is necessary for determining the appropriate size of the pump required, and knowledge of the magnitude of frictional losses is of great importance because it determines the power requirements of the pump forcing the fluid through the pipe. For example, in refining and petrochemical industries, these losses have to be calculated accurately to determine where booster pumps have to be placed when pumping crude oil or other fluids in the pipes to a distances thousands of kilometers away. And pipe flow can be stated as the closed conduit flow of fluid under certain pressure. A typical pipe flow is shown in this figure here. This is the typical pipe flow. And for a pipe completely full of flowing fluid, the velocity is maximum at the center. If you look at this case or laminar case or the turbulent case, the velocity is the maximum at the center here, center of the pipe, and is zero at the solid surface. If you move towards the wall, that is from the center towards the wall, this side as well as this side, the velocity go on decreases. Okay. So this is the velocity profile of a laminar and turbulent flow, and because of this velocity gradient from the center towards the wall of the pipe, a velocity gradient exists because of what? The relative motion between the fluid layers. That is, the velocities of different layers will be different from the center. Okay. So because of this velocity gradient, there exists a shear stresses between the fluid layers as well as between the fluid and the solid boundary. Hence, there is an energy loss. So, as I mentioned, pipe losses in the piping system results from a number of system characteristics which include among others, that is a pipe friction, changes in direction of flow, obstruction in flow path, and the sudden or gradual changes in the cross section and shape of the flow path. So this is about what the call as a flow through a pipes. So in this particular uh, chapter, so both we are going to learn laminar as well as the turbulent flow through the pipes, and also different types of losses, namely the fluid friction losses, that is also called as a major losses, and losses due to abrupt changes in geometries and pipe fittings, which is also called as a minor losses, are to be discussed. Then the different types of piping systems are to be discussed. As I mentioned previously, so whenever a fluid starts flowing through a pipe, so there exists a resistance to motion. So when a fluid flows through a pipe, the internal roughness of the pipe wall can create, like this, the internal roughness of the pipe wall can create a local eddy currents in case of a laminar as well as a turbulent. Because of this local eddy currents within the fluid adding resistance to the flow of the fluid, then the velocity profile in a pipe will show that the fluid elements in the center of the pipe will move at a higher speed than those closer to the wall. Therefore, a friction will occur between the layers. So because of this velocity gradient, the friction will occur uh, between the layers within the fluid. So this moment of fluid elements relative to each other is associated with a pressure drop called frictional losses. Then pipes with a smooth walls such as a glass, copper, brass and polyethylene have only a small effect on the frictional resistance. Then pipe with a less smooth walls such as concrete, cast iron and steel will create a large eddy currents which will sometimes have a significant effect on the frictional resistance. So the rougher the inner wall of the pipe, more will be the pressure loss due to friction. And as the average velocity increases, pressure losses increases, like this. As the average velocity increases, the pressure losses get increases. That is, velocity is directly related to the flow rate. So as the average velocity increases, the pressure losses increases. Then the velocity is directly related to the flow rate. Therefore, the velocity is given by volumetric flow rate, so divided by the cross-sectional area of the flow. So an increase or decrease in the flow rate will result in a corresponding increase or decrease in the velocity. Smaller pipes causes a greater proportion of the liquid to be in contact with the pipe, which creates a friction. When pipe size also affects the velocity. Given constant flow rate, decreasing pipe size increases the velocity, which increases the friction also. The friction losses are cumulative as the fluid travels through the length of the pipe. The greater the distance, the greater the friction losses will be. So fluids with high viscosity will flow more slowly and will generally not support the eddy currents, and therefore the internal roughness of the pipe wall have no effect on the frictional resistance. So this condition is known as laminar flow. Therefore, there are in general there are three types of flows in pipes generally we come across. There is the laminar flow. As we come across generally, there is a laminar flow and also the laminar and turbulent flow, and even a transitional flow. So what is a laminar flow? The fluid particles move along a smooth, well-defined path or streamlines that are parallel. Thus the particles move in a laminas or layers, smoothly gliding over each other, and this type of flow is called as a laminar flow. So example, flow of blood in a small veins can be classified as a laminar flow. Even the flow in which the adjacent layers do not cross to each other and move along the well-defined path is called as a laminar flow. You can look at this animated picture here. Fluids layers are moving in a well-defined path when the velocity of the fluid layer will be maximum at the center and it is gone decreasing towards the wall of the pipe. This is towards the wall of the pipe. Hence, the velocity profile will be a parabolic. So, laminar flow generally happens when dealing with the small pipes, low flow velocities, and with the highly viscous fluids. At low velocities, fluids tends to flow without lateral mixing, and adjacent layers slide past one another like playing cards. So there are neither cross currents nor eddies in case of laminar flows. Laminar flow can be regarded as a series of liquid cylinders in the pipe where innermost parts flows the fastest and the cylinder touching the pipe isn't moving at all. So that is called as a laminar flow. Okay. So this is the flow we can uh, show here. This is a laminar flow. The turbulent flow. What is turbulent flow? So turbulent flow means the flow in which the adjacent layers cross each other and do not move along the well-defined path is called as a turbulent flow. Example, flow through a river or canal, smoke from a chimney is also classified as a turbulent flow. So in turbulent flow, the fluid moves erratically in the form of a cross currents and eddies. Turbulent flow happens in general at high flow rates and with larger pipes. So this is the flow profile types. So the first profile shows a laminar flow. So all the fluid particles are flowing in a well-defined path without mixing. They are parallel to each other. And next, the third profile is a turbulent profile. that is all the fluid particles get mixed and they are moving in an erratic manner, and in between one more state called as a transitional state. So transitional flow is a mixture of laminar and turbulent flow. So this one is a mixture of laminar and turbulent flow within a turbulence in the center of the pipe and laminar flows near the edges. So means this is a mixture of laminar and turbulent flow with turbulence in the center. You can see the center and laminar flow near the edges. So each these flows behaves in different manner in terms of their frictional energy loss while flowing and have a different equations that predict their behavior. So Reynolds studied the conditions under which one of the flow changes into the other and found that the critical velocity at which the laminar flow changes into turbulent flow, it depends on four quantities. He studied, that is Reynolds has studied, and he concluded when the laminar flow changes into turbulent flow, it depends on the four quantities, that is the diameter of the tube, the viscosity, density and average velocity of the liquid. And also he found that these four factors can be combined into a one group and that the change in a kind of flow occurs at a definite value of the group. So the grouping of the variables so found was Reynolds number. So the turbulent or laminar flow is determined by the Reynolds number. So this is how the flow profile types can be classified as a laminar, transitional and turbulent. These flow profiles can be identified by using the Reynolds number, and hence a Reynolds experiment can be explained further. So Reynolds experiment is used to identify the type of flow through a pipes, that is a laminar and a turbulent flow. So the laminar flow has been discussed previously, that is in a laminar flow the fluid particles move along a straight parallel path in layers or laminas such that the paths of the individual fluid particles move along the direction of flow and they do not cross each other, those of the neighboring particles. Then the laminar flow is possible only at low velocities and when the fluid is at highly viscous. But when the velocity is increased or the fluid is less viscous, then the fluid particles do not move in a straight paths. Then the fluid particles move in a random manner, resulting in general mixing of the fluid particles. And this type of flow is called as a turbulent flow. So to identify this, that is laminar and turbulent, Reynolds has demonstrated an experiment, and that experiment now we are going to discuss. So Reynolds experiment, so this is the setup for the Reynolds experiment. So the apparatus consists of a tank containing a tank containing water at a constant head. This is the tank containing a water at a constant head, and one more a small tank, this one containing some dye, that is a colored water, and a glass tube having a bell mouth here. This one, a glass tube. This is the glass tube having a bell type orifice, that is a bell mouthed entrance at one end, and a regulating valve. Here this is the regulating valve, a regulating valve at the other ends. Then the water from the tank was allowed to flow through the glass tube. Then the velocity of flow was varied by the regulating the valve. A liquid dye, that is the colored water, having the same specific weight as that of water, was introduced into the glass tube, and as shown in this figure here. So the following observations were made by the Reynolds. So he made some of the observations. So they are, when the velocity of flow was low, set very low, the dye filament in the glass tube, the dye filament in the glass tube here. First one, the dye filament in the glass tube was in the form of a straight line, and this is stable also. This straight line of dye filament was parallel to the glass tube, which was the case of laminar flow. This one, the dye followed at a very low discharge. He observed this dye filament, he observed that dye followed a straight path, which was the case of laminar flow. And the second observation he made, with increase of velocity of flow, that is for the medium discharge, a little increase in the velocity of flow, the dye filament was no longer a straight line, but it became a wavy one, like this. It became a wavy one, like this. It became a wavy one as shown in this figure here. This shows that the flow is no longer laminar. So means a dye followed a wavy path and with a streak intact, and he called that state as a transitional state or transitional flow. So third observation he made, with further increase of velocity of flow, the wavy dye filament, this one, the wavy dye filament broke up and finally diffused in water. So you can see in this figure, finally diffused in water like this. It is got mixed up completely. So this means that the fluid particles of the dye at this higher velocity are moving in random fashion, that is in a zigzag manner also, which shows the case of turbulent flow. This shows the case of turbulent flow. Thus, in case of a turbulent flow, the mixing of dye filament and water is intense and flow is irregular, that is random and disorderly. So the dye rapidly mixed through the fluid in the tube. So in case of a laminar flow, the loss of pressure head was found to be proportional to the velocity, but in case of turbulent flow, the Reynold observed that the loss of head is proportional to the square of the velocity. So in this case, the first case, he observed that the loss of head is proportional to the velocity, that is in the case of a laminar flow, and in case of a turbulent flow, he observed that the loss of head is proportional to the square of the velocity. It was square of the velocity. So square of the velocity, like this. So these are the observations this Reynolds has made, and based on his observation, the flows are being classified as a laminar flow and transitional flow and turbulent flow. So these are the some of the observation made by the Reynolds, as I explained previously. At very low velocity, or you can call it as a low discharge, the dye will move in a line parallel to the tube, and also it does not get dispersed, and this dye filament was straight, parallel and stable. At this state of flow he called as a laminar flow, and at velocity little more than before the dye moves in a wave form. So like this, it is wavy filament. That state he called as a transitional state, and at more velocity the dye will no longer move in a straight, and that state he called as a turbulent flow. That is this completely the diffused filament, this one is, and that state he called as a turbulent flow. Then what is Reynolds number after that? So the number that is called as a Reynolds number, it is the ratio of inertia force to viscous force, is said to be the Reynolds number, that is this one. So Reynolds number is represented by NR or some or Rn. It is the ratio of inertial force, that is Fi, divided by viscous force, Fv. Fi divided by, that is Fi, inertial force divided by viscous force. So finally we get, when we substitute the inertial force and the viscous force, and if you simplify this one, we get rho Vd by mu, and also we know that the kinematic viscosity is the ratio of, that is mu is the ratio of dynamic viscosity by density of the fluid. If we substitute here, we get this one, that is Vd by nu, where V is the mean velocity in the pipe, and D is the pipe diameter, rho is the density of the flowing fluid, and mu is the dynamic viscosity, and nu is the kinematic viscosity. Okay. This is the Reynolds number. Then based on the Reynolds number, so the flow can be identified through a pipe as, suppose this is the equation for the Reynolds number. If this Reynolds, that is equation, comes out to be, say, if suppose the Reynolds number is more than 4000, it is called as a turbulent flow, means unpredictable, the rapid mixing. Then for that we get a number as more than 4000. If it is in a transitional state like this, wavy form like this, and that is called turbulent outburst, and the number is in between 2300 to 4000. If the Reynolds number comes to be less than 2300 or less than 2000, then that state what we call as a predictable and slow mixing, and that is called as a laminar flow. Okay, so means if Reynolds number is less than 2000, it is called as a laminar flow. If it is more than 4000, it is called as a turbulent flow, and if it is in between 2000 and 4000, that is called as a transitional state or transitional flow or turbulent outburst. And for you can look at the graph here, that is head loss versus, that is HF versus the velocity. For the up to here it is a laminar flow, to here laminar flow, and here up to here it's a laminar flow up to here, and here this is the wavy, means there is a transition. We're getting here there is a transition. Up to here is a laminar and up to here is a transition. This is a transition, then it is turbulent. For the laminar flow, the head loss is proportional to the velocity, and for the turbulent, the head loss is proportional to the velocity square. Okay, so proportional to the velocity square, that is square of the velocity. So they are here they written h is proportional to the u raised to n, that Vn value is an index, it varies from 1.5 to 1.5 to 2. Okay, this is the graph. Then pipe flow characteristics are dependent on the value of the Reynolds number. So whenever the fluid starts flowing through a pipe, the characteristics of the flow through a pipes are dependent on the Reynolds number, that is rho Vd by mu. That is, this is the Reynolds number. Suppose if Reynolds number comes out to be more than 0 and less than 1, it is a highly viscous laminar flow, but that flow is creeping flow, creeping motion. It's a very slow motion, that is when we get Reynolds number is less than 1. If Reynolds number comes out to be more than, if it is in between 1 and 100, that is laminar, strong Reynolds number dependence. If Reynolds number is in between 100 and 1000, it's a laminar flow only, but boundary layer theory useful here. If Reynolds number is in between 1000 and 10,000, that is a transition to the turbulence. If Reynolds number is 10,000 to 10 lakh, then it is a turbulent, moderate Reynolds number and dependence. If Reynolds number is more than 10⁶ and less than infinite, it is a turbulent, slight Reynolds number dependence. So these are some of the flow characteristics which are dependent on the Reynolds number. So the significance of Reynolds number here, as we know the significance of Reynolds number is used to identify the type of flow through a pipes, whether the laminar or a turbulent. So the definition of Reynolds number here, the Reynolds number is what? This is the Reynolds number, that is, it is a ratio between the inertial and viscous. So when we simplify that equation, we get as a rho Vd by mu. So the Reynolds number can be interpreted as the ratio of inertia to viscous effect. So one of many interpretations. So at low Reynolds number, that is viscous effect is comparable to inertial effects. Flow behaves in orderly manner, that is a laminar flow at very low Reynolds number. And at high Reynolds number, the viscous effect is insignificant compared with the inertial effect. Then the flow pattern is irregular, unsteady and random, that is turbulent flow. So in very simple manner, we can say the significance of Reynolds number is just to identify the type of flow through our pipes, whether the laminar or turbulent. Then laws based on the Reynolds number, the laws of fluid friction can be defined or can be given as such different laws are obeyed by a frictional resistance in the laminar and turbulent flows. Means whether the flow could be a laminar or turbulent, there could be a frictional resistance in the flow system. So on the basis of experimental observations, the laws of fluid friction for two types of flows may be narrated as follows. The laws of fluid friction for a laminar flow. So frictional resistance in a laminar flow is proportional to the velocity of flow, then independent of pressure. Means if the flow is a laminar, it is proportional to the velocity of flow, that is frictional loss is proportional to the velocity. Independent of pressure, it is not depending on the pressure at all, and independent of the nature of the surface in contact also. So the irrespective of the surface, the head loss is proportional to the velocity. It is independent of the nature of the surface in contact, and it is proportional to the area of the surface in contact. So area of the surface in contact then greatly affected by the variation of temperature of the flowing fluid. Then laws of fluid friction for a turbulent flow. So proportional to the velocity raised to, that is proportional to the velocity power, that is raised to n, where the index n varies from 1.72 to 2. It is independent of pressure and proportional to the density of the flowing fluid, and slightly affected by the variation of the temperature of the flowing fluid, since so the fluid molecules are having intermolecular force of attraction. As the temperature increases, the force of attraction breaks, so hence the viscosity get decreases. So that's why the slightly affected by the variation of temperature of the flowing fluid, then proportional to the area of the surface in contact. So it mainly depends upon the surface in contact, then the dependent on the nature of the surface in contact, proportional to the area of the surface in contact, as well as dependent on the nature of the surface in contact. Then the loss of energy in pipes. So there are mainly two types of losses will occur in a pipes. They are major energy loss and minor energy loss. So regarding this loss of energy in a pipes, so we'll discuss in detail in the next class. Thank you.